this is a question on radioactivity. But before we start, let's try to relate all the equations together in sort of like a mind map to show how every physical quantity are related to each other. So usually when I talk about radioactivity, right, I will use this particular equation as the junction, sort of the junction that connects all the physical quantities related to radioactivity. So usually I'll start with the equation saying that the activity is equals to the decay constant multiplied by the number of radioactive nuclei. I think this equation is very strong, very powerful equation because it relates between the activity, which is basically the rate of decay. You relate it with the number of radioactive nuclei, which is another thing. Okay, number of radioactive nuclei, you are counting how many nuclei you have, but activity is talking about how many decays is happening per second. So this equation sort of relates between the two things, and later on you see how I expand from this equation to see how the other equations are related to each other. Okay, so I'll be labeling A as in blue, but I will change the lambda and the n to be different color to make everything clearer how they relate to each other. So lambda, I'll do it in green, whereas the number of radioactive nuclei I'll do it in red. Okay, so the activity over here, sometimes we also call it as decay rate. So you should expect that occasionally you should see the equation to be written as negative dn over dt. Okay, dn dt, this value here is the change of number of radioactive nuclei per unit time. So let's say if you see 5 decays happening per second, that means by the number of radioactive nuclei decreased by 5, because 5 radioactive nuclei have already decayed, right? So the number of radioactive nuclei has already decreased by 5 per second. So saying activity is similar to decay rate is okay. Okay, activity is basically decay rate, the rate of decay, and is equivalent to the decrease in the number of radioactive nuclei per unit time. But there's a negative sign because decrease is negative in value, right? So this dn dt here is usually negative in value, but multiply by a negative in order to get an activity which is a positive value, because activity is focusing on how many decays happening per second. So if I say 5 decays happening per second, then A is equals to 5 per second. But dn dt here is how much is the change of number of radioactive nuclei. So because it's decreased by 5 per unit time, so it's negative 5 per second. So negative 5 per second multiplied by the negative, you get a positive 5 decay per second. That's how you relate between them. So because you understand this already, then you can say that it's equals to, of course, lambda n is the same thing. Okay, so lambda n over here. Okay, so this is the equation that relates the two different things, A and N. So let's try to look at the left hand side. What kind of things can we talk about when we talk about activity? So when we talk about activity in specific, usually we relate it to how does activity change with time. So how does activity change with time? We know that the activity should decrease exponentially with time, because there's less and less number of radioactive nuclei left, so the intensity of the activity should also decrease with time, and this is represented by this equation. A is equal to A naught e to the power of negative lambda t. So this equation tells us how does the activity changes as the decays progress. Okay, so there's a graph for this equation as well. This graph shows us how does the activity changes with time. So it's activity against time, so the graph should decrease exponentially with time, starting with A naught, the initial activity. Okay, so that's for the blue side of things. Next, let's move on to the green side. Okay, the green is decay constant. If you have a greater decay constant, then that means your material decays faster. If you have a smaller decay constant, that means your material decays slower. Okay, so each type of material, let's say for this question is 57 cobalt. 57 cobalt has its own decay constant. 238 uranium has its decay constant. Every single radioactive material, they have their own decay constant. And this decay constant, we can relate it to half-life. So usually we will say half-life T half is equals to ln 2 divided by lambda. Okay, if you're interested to know derivation can be, you can refer to the explanation video. Here I'm just trying to show you how all the equations can relate to each other. Okay, so half-life is T subscript half is equal to ln 2 divided by lambda. Why is it ln 2 divided by lambda? Is because radioactive decay is actually a first order reaction. So if you learn about first order reaction and the equations behind it, then you can derive this equation. Half-life is equal to ln 2 over lambda. Okay, so from here lambda can relate it to half-life. Okay, lambda relate to half-life. Okay, next, for the right hand side of things, how do you relate, what kind of equations are related to the number of radioactive nuclei? So if you are focusing on the number of radioactive nuclei, there are two equations that you should take note that relates to number of radioactive nuclei. The first one will be similar to what you see on the left, which is how does the number of radioactive nuclei changes with time. So we know that as decay goes on, the number of radioactive nuclei should decrease with time. So if the number of radioactive nuclei decrease with time, you should expect a similar pattern for how the number of radioactive nuclei changes with time. It should be similar to how does the activity change with time. Because as you know, this is A is proportional to N, right? So if A decrease exponentially like this, the number of radioactive nuclei should also decrease exponentially like this. Okay, so this sort of shows you how does the number of radioactive nuclei changes with time. But there's another thing that there's another equation which is quite important in our syllabus. For the number of radioactive nuclei, sometimes they choose to not be so straightforward, giving you the number of radioactive nuclei. What you need to do is you need to derive it from the mass of the radioactive material. So let's say they'll give you, there are 400 grams of uranium-238. So that's uranium-238, that's 400 grams. So you need to, when you see that they give you a mass, right, you have to deduce this mass, this amount of material, this mass of material is equivalent to how many radioactive nuclei. When they give you terms in mass, you always need to switch it back to the number of radioactive nuclei. So how do you relate to the number of radioactive nuclei? Well, you can take the mass of the radioactive material that you have, divide by the molar mass. Okay, this term over here, mass of the material divided by the molar mass, will give you the number of mole of the radioactive nuclei. How many moles you have for the radioactive nuclei. Then for each mole, you know that there's Avogadro number of radioactive nuclei. So you multiply by the Avogadro number. That will tell you in total how many radioactive nuclei do I have. So this equation here will tell you how to determine the number of radioactive nuclei from the mass. But this one, I think many students always tend to forget that this M here represents the mass of material. Mass of radioactive material. Okay, whereas the big M underneath it, it's usually, it's not usually, it is the molar mass. Okay, but molar mass, if they don't give you the molar mass specifically, you can get it from the number of nuclei. Okay, let's say uranium-238, right? Uranium-238, 238 is a nucleon number, right? So nucleon number is 238, usually that means the molar mass is 238 gram. We assume one nucleon to be 1 U. So if it's 238 nucleon, then the mass will be 238 U for a single uranium-238. Then if you convert it to molar mass, that will be equivalent to 238 gram. Okay, so that's how we usually get the molar mass. You will get it from the number of nucleon, just put it in the unit of gram, then that will usually be the molar mass. Okay, but I think it's better that they give it specifically because sometimes there's some decimal places to it, right? But to get a rough idea, if they don't give you this molar mass, you can obtain it from the mass number or this number of nucleon over here. Okay, so that's how everything relates to each other. Actually, you have one main equation. For the left hand side, can relate to how the activity change with time. For the right hand side, can relate to how does the number of radioactive nuclei change with time. And if you don't have the number of radioactive nuclei, you have to derive it from the mass of the material being given. And this decay constant here can also be related to half-life. So this is how you piece everything together. Okay, so yeah, let's another thing you need to be careful about is the conversion factor. Okay, so this is mind map for equation. Next, there's also conversion, unit conversion, sorry. Next, there's unit conversion of activity, or you can call it as decay rate. Yeah, basically similar thing, just whether there's a negative. No, it's the same thing. Don't worry too much. It's the same thing. Okay, so one thing you need to know is 1 Curie, okay, is equivalent to 37 billion becquerel. Okay, then what is 37 billion becquerel? 37 billion becquerel is equivalent to 37 times 10 to the power of 9 per second. So this much of decay happening per second is equivalent to 1 Curie. So if you have an activity of 1 Curie, that means by there's 37 billion decay that happen per second. Okay, so if you understand the mind map for equation that relates between this 1, 2, 3, 4, 5 equation and the unit conversion for activity, I think you should be able to sail through all the questions within our syllabus quite easily. Okay, so let's look at this question over here. The radioactive isotope of 57 cobalt decays by electron capture. So electron capture is something not within your syllabus, but it's a kind of decay, similar to what you have for alpha decay, beta minus decay, beta plus decay, so on and so on. They tell you that this 57 cobalt, they decays with a half-life 272 days. Okay, each type of radioactive material, they have their own half-life, they have their own lambda. Okay, so now find the decay constant. Decay constant is lambda. So how do you obtain lambda from half-life? Well, half-life is over here, lambda is over here. How do you relate them? Is this equation over here. Okay, so let's try to solve question A. Question A, you can use half-life is equals to ln 2 divided by lambda. Okay, so here you have to be very careful. You have to be very careful with what? Always be consistent with the time unit. Here, when you're substituting a half-life, if you choose to substitute 272 right away, you have to be very clear that your calculation right now is in days. So if your calculation is in days, later ln 2 here is dimensionless, right? This natural log here is dimensionless. There's no unit to it. So when you calculate your lambda should generate an answer of 2.548, 2.548, sorry, times 10 to the power of negative 3. Okay, now think about it. If you take natural log of 2, which is no unit, which has no unit, divide by 272 days, which has a unit of days. Days is now the denominator, so the unit over here should be per day. Per day, there's this much, or there's this decay. Okay, there's this decay constant, but it's in the unit of per day. Okay, but if you're not comfortable with leaving your answer as per day, you want to change it to SI unit, then you need to do some unit conversion over here. So if I want to do unit conversion, this is where you need to be very careful. You can see that the per day has a -1 over here, so means by if you want to do conversion, you should bring the day down at the denominator. So now if you want to convert, you should eliminate day, convert it to SI unit, so that will be in second. So second, put it down here. So one day, how many seconds do you have? One day there's 24 hours. Each hour you have 60 minutes in it. Each minute you have 60 seconds in it. So this is how you do your conversion, and you're able to get the answer, which is 2.949 times 10 to the power of -8 per second. Okay, so make sure to keep track of the time unit very carefully. If you put in your half-life in days, then your decay constant, your lambda, will be per day. Okay, of course you can easily switch it around to per hour, to per minute, or even to per second. So that's just basic unit conversion. Okay, question B, if you have a radiation source containing 57 cobalt, okay, with an activity of 2.00 micro Curie, how many radioactive nuclei does it contain? So this thing here, activity here, it's A, right? okay, and they ask you for how many radioactive nuclei does it contain. How many radioactive nuclei means by the number of radioactive nuclei. So this is n. So how do you relate a and lambda? A and n together is by a is equals to lambda n. So this lambda, we need to use this lambda that we have from the previous sub-question, apply inside to obtain our number of radioactive nuclei. Okay. So again, be very careful with the time unit that you put in. So a is equal to lambda n. You know that your lambda over here is in per second. You know that n over here has no unit. So n has no unit. Lambda has per second for its unit. So the activity here should also have per second for its unit. Per second is equals to per second multiplied by no unit. Okay, that only makes sense, right? So if you want the activity to be in per second, activity, if it's in per second, you have to put it into the unit of becquerel. But right now you're given activity in the unit of microcurie. So you have to change it from microcurie to becquerel. That only you are able to put in your lambda properly to get your n. So you have 2 microcurie, 2 times 10 to the power negative 6 curie. But of course, you are not supposed to substitute it in curie. You have to convert it to becquerel in order to put it in per second unit. Okay, so 1 curie is equivalent to 37 billion becquerel. So this will allows you to obtain your activity in per second already. Right now, you can substitute your lambda. Your lambda is 2.949 times 10 to the power negative 8. Of course, you have a choice to put in either 2.949 times 10 to the power negative 8 or 2.548 times 10 to the power negative 3. But I think you can see that it's more convenient to substitute in the decay constant in per second, because our activity right now is also in per second once we have converted it to becquerel. Okay, of course you can change the activity to per day, but that means you need to do another even more unit conversion, which is quite inconvenient. So we stick to the usual unit conversion, convert it to per second, but we use the decay constant. Make sure we use the decay constant in per second as well. Okay, so this is your lambda multiplied by n. Okay, so if you calculate everything, you should get the number of radioactive nuclei to be 2.509 times 10 to the power of 12 nuclei. Okay, you can write down the unit. Technically, there's no unit to it, but if you want, you can write nuclei. So that means that there's this many number of nuclei in the material. Okay, next. What will be the activity of your source after 1 year? So this one, they relate with time. They want the activity. You have the previous activity. The initial activity is 2 microcurie, but now they're interested with after 1 year, how much is your activity? Okay, so if you want to relate activity with how it changed against time, you need to shift to the equation that relates activity and how it changed with time. So this is question C. You know that you need to solve it using A is equals to A naught E negative lambda T. Okay, so here you have a few options of how you want to do. Basically, you need to make sure lambda and T over here, their unit has to be consistent. This pair, the unit has to be consistent. And for activity and activity naught, this pair also the unit has to be consistent. Okay, the time unit has to be consistent. Okay, let me write more specifically. The time unit has to be consistent. This one, the time unit also has to be consistent. But between these two, right, not necessarily the same. You can have activity in per second, but you can have your lambda and T in days. Okay. Not necessarily the same. Okay, so means by if I can actively choose to take A and A naught over here, the activity to be in becquerel or in curie, there's no problem to it. And I can be different. I can use lambda and T here to be in per days and days, or in per year and year, or in per hour and hour. I can not necessarily follow per second over here. I can do it in per second for the activity, but in per days for the lambda and T. Okay, I just need to make sure lambda and T, between them, they are consistent. Between A and A naught, they are consistent. But between A and the lambda T over here, they are not necessarily the same time unit. You are able to do it. Okay, so let me demonstrate what does it mean by I can be inconsistent between A and the lambda t. Well, for A over here, maybe I choose to do it in Curie. I can do it in Curie. If I want to do it in Curie, then the initial activity will be 2 micro. Right now, this is a totally different unit, right? Becquerel is not per second. Curie is not per second. Becquerel is per second, but Curie is not per second. So we can see that activity here, I'm not using per second. Okay, I'm using Curie. Okay, but for the lambda and t, I need to make sure between lambda and t, they have to be consistent. So if I wish to use 2.949 times 10 to the power of 10 to the power negative 8, I need to put my time here to not be 1 year. I have to change it to 1 year equivalent to how many seconds. So I have to do 1 year has 365.25 days. Each day there's 24 hours. Each hour there's 60 minutes. Each minute there's 60 seconds. I have to convert 1 year to be seconds. Okay, if I wish to use lambda in the unit of per second. But I think you can see that it is more convenient if I use lambda in per day instead. Because if I use lambda in per day, my time you need to substitute in unit of days, and 1 year there's just 365.25 days. So that will be more convenient for us. So our lambda, I'll take 2.548 times 10 to the power of negative 3. That'll be my lambda. Then for my time will be 365.25 days. Okay, so this one 2.548 times 10 to the power negative 3 is in per day. 365.25 is in day. So between them, their time unit is consistent, which is day. But they are not necessarily consistent with the activity, which is in the Curie over here. Okay, so that is the main point I want to deliver. Not necessarily consistent between activity and the lambda t over here. But between lambda and t, they need to be consistent. Okay, why 365.25? Why not 365? Why not 366? Is because once every 4 years there's a leap year, right? So leap year is 366 days. So there's an extra 1 day, but it happens every 4 years. So we split it 1 day to 4 years. So each year will get an additional a quarter of a day. So 365.25. Okay, so if you calculate everything here, you should get your answer to be in unit of Curie. Okay, because you are calculating activity. So the activity after a year is 0.79 times 10 to the power negative 6 Curie. Okay, but if you choose to, you can choose to convert it in Becquerel as well, because sometimes people prefer in Becquerel. So you can do it by eliminating Curie, introducing Becquerel, and you know that 1 Curie has 37 billion Becquerel. So if you do a unit conversion, you get your answer also in Becquerel. So this is 2.92 times 10 to the power of 4 Becquerel. So if you write your answer in Becquerel, that's correct. If you write your answer in per second, that is correct as well. Okay, but usually I write in Becquerel. Okay, so this is how we determine the activity at a later time. And this is how we solve everything. And I think we use many equations over here. We have used this center equation, this equation, and this equation over here. So this mind map I think is sort of useful because it tells you how every quantity is related to another quantity through this map over here. And that's it for this question over here. Thank you very much.